Electrons are bound to nuclei to form atoms by the Coulomb force. But imagine a world where electrons and protons were uncharged, and all that bound an electron to a proton in the atom was the gravitational force between them. What would such a world look like? Suppose an electron was bound to a proton, as in the hydrogen atom, by the gravitational force rather than the electric force. Assume that the electron and proton have no charge. Calculate the radius and energy of the first Bohr orbit. The key concept here is that both the gravitational potential and the Coulomb potential result in central forces. In fact, their potentials take the same form. They have the same R dependence, which I've written here. This constant C for the case of the Coulomb force is Ke squared. I've taken out the minus sign, which denotes the fact that for an electron and a proton, this is going to result in an attractive force. And of course, the force of gravity between a proton and an electron is attractive, and this constant C would be g times the mass of the proton times the mass of the electron. G is Newton's constant, which I've given in the attached PDF to this problem. We'll use Bohr's model for this of the atom for this problem. So the electron orbits the proton, and its allowed values of orbital angular momentum, MVR, are quantized. They're labeled by this quantum number n, which takes positive integer values. Okay, so step one, we want to solve for the energy of the first Bohr orbit, that's n equals 1, for this system for the case of a gravitational potential holding the electron to the proton rather than the Coulomb potential holding the electron to the proton. But since these have the same form, I'm going to write everything in terms of C so that we can compare at the end. So the total energy is, of course, the kinetic plus potential energy. The kinetic energy is the kinetic energy of the electron going around the proton, 1/2 mv squared. And the potential energy is just minus C over R, where we'll plug in C later for these constants. Newton's second law, F equals ma, tells us that the force that results from these central potentials, so that's given by the gradient of these potentials, which goes like C over R squared, is equal to the mass times the acceleration of the electron, which is the centripetal acceleration, since it's going around in a circular orbit. So that's m times of the electron times v squared over r is that centripetal acceleration. And we can use this relation to solve for the kinetic energy of the electron. So I can just rearrange this a bit to solve for 1/2 mv squared, which will be equal to C over 2r. Good. So plugging that in to the total energy, we'll find that the total energy in terms of this constant C and the radius r of the orbit is minus C over 2r. So next we want to solve for what this radius is for the first Bohr orbit. So there's going to be a different radius for different orbits, different quantum numbers n. We can do this by combining this equation of the quantized angular momentum with this equation that we derived for the kinetic energy. So we can use these equations to get rid of the velocity v and solve for r in terms of the other constants that we know. The result of this, so over here I'm going to write the results for n equals 1. Then combining these two equations, I would get r for n equals 1 equals h bar squared over the mass of the electron times c. So these radii are quantized. Plugging in to the energy, we can get the energy of the first Bohr orbit, which I'll call E1, the energy for the n equals 1 orbit, And just plugging this into here, what we'll find is this is minus the constant c. This is not the speed of light. This is our constant over here, times c squared times the mass of the electron over twice h bar squared. So I've given the values of all of these constants in the attached PDF. And what we find, plugging in these values for the electric force, the Coulomb force, is that this energy is, of course, as we'd expect, minus 13.6 eV. Note that the minus sign reflects the fact that this is a stable bound state of the system, meaning we need to add energy to the system to kick the electron out of its stable first Bohr orbit. And also plugging in the numbers, as we'd expect for the Coulomb force, this is the standard result, that the electron in the first Bohr orbit is at the Bohr radius, A0, which in terms of numbers is 5.3 times 10 to the minus 11 meters. Now, before we plug in the numbers for the case that we're interested in, which is an electron bound to a proton just by the gravitational force between them, let's think about what we would expect. If we plug in for what c is over here in the potential for the case of the Coulomb force, just to get an order of magnitude estimate of the difference between the Coulomb potential and the gravitational potential, we would get something like 10 to the minus 28 Newton meters squared per over r. And if we plugged in for c gravitational here instead, we would get something on the order of 10 to the minus 67 Newton meters squared over r. So this is telling us that the gravitational force is going to be much weaker than the electric force between the electron and proton. This is 39 orders of magnitude smaller than the electric potential for a given radius r. And this reflects the fact that the gravitational potential goes like the mass of the proton times the mass of the electron and is very weak for the very small masses of these objects. So what we would predict is, since the gravitational force between the electron and proton is so much weaker than the Coulomb force, is that the electron would be found at a much larger radius because it's more weakly bound. So we can see if that's the case. Now plugging in the numbers for the case of c gravitational, which I do in the attached PDF, we would find an energy of minus 2.7 times 10 to the minus 78 eV. This is a vanishingly small energy. And this radius turns out to be 1.2 times 10 to the 29 meters. So like we predicted, this is a larger radius than the Bohr radius. It is much larger. This is a huge number. This is actually on the order of the size of the observable universe. So, which is reflecting the fact that the force of gravity between these particles is much weaker than the Coulomb force. Okay, so there are two takeaways from this problem. The first point to make is that this calculation demonstrates why it's okay to ignore the gravitational force between an electron and a proton in a hydrogen-like atom. It just is irrelevant compared to the much stronger Coulomb force between them. And the second point is that we are the size we are, and not astronomically huge, because we are bound by the electric force.